Okay, we're back to talk more about torque. So we just got done saying that linear motion quantities have angular correspondence, for lack of a better word. Linear displacement, angular displacement. D turns into theta when we're talking about angular motion. V becomes omega, A becomes alpha, and when we're talking about forces, the angular analog or equivalent, not equivalent, I shouldn't say equivalent, but the angular analog, the partner to that, is torque. Okay? So, quick note of description. Forces and torques are similar, but not exactly the same. An object's linear acceleration depends on only force, magnitude, and directions. Magnitudes, I guess. But angular acceleration, the rate at which angular velocity changes per second, depends on these things plus where the force is applied. Okay, just like we talked about up here. Torque depends not only on how strong the force is and the angle at which the force is applied, but also the displacement vector between where the force is applied and where the axis of rotation is. Okay, so they're similar, but forces and torques are not quite the same. All right. So we also, let's see here, what happens when there are multiple torques on an object? What if there's multiple things trying to influence how the object rotates or twists or turns? Well, again, what you'll see me do in this unit is constantly refer back to, well, what did we do when we learned about linear motion? When we had multiple forces acting on something, and we're talking about linear motion, if we had multiple forces, what we did was we found the net force, the sum of all the forces. And the way we did that was F net equals MA, which was really equal to, well, plus or minus the first force, plus or minus the second force, plus or minus the third force, plus or minus ... until we got to the end of the forces. In other words, we drew a free body diagram, we determined whether, based on an axis, whether a force was going to be positive or negative, and then we added or subtracted them appropriately. We do a similar thing with angular motion. If we have multiple torques, we find what is called the net torque, the sum of all the torques. Net torque, sorry, that's a colon. So we find torque net. It's not equal to M times A, it's equal to I times alpha. And what it's really equal to, again, is plus or minus the first torque, plus or minus the second torque, plus or minus the third torque, and so on and so forth, depending on our axis. One thing I do have to explain is what this I thing is. I stands for something called the moment of inertia. The moment of inertia is how hard it is to rotate something based on shape, mass, and the axis of rotation. Okay, so again, I guess you could kind of say that the linear quantity of mass has an angular analog in I, the moment of inertia. It is partially based on mass, but it's also based on shape, and it's also based on what you choose to be the axis of rotation. This isn't going to be a great example because, well, actually, here. I got a good example, I think. Let me go and get it. Okay. Let's see here. How do I want to do this? I'm going to take the camera. Okay. So, I've got this broom here. All right? So, moment of inertia essentially refers to how easy it is to rotate something about an axis. To rotate this broom, imagine there was an axis going straight through the main kind of center pole of the broom. It's very easy for me to rotate the broom like this, okay? The reason is most of the mass is distributed very close to the center to the axis of rotation. However, so I can do that with one hand very easily. It would be much harder for me to try to rotate this broom. I have to put a lot more effort in to try to rotate this broom about an axis that goes through the handle, let's say, this way. So in other words, if I wanted to pick up this broom and basically eventually get the broom part of this above, I could rotate it like this with one hand very easily. It is almost impossible for me, using just one hand, to rotate this broom like this. I really have to put some effort into it, okay? Really, really difficult. So, that's a little bit about about moment of inertia. What's happening there is, the reason it's harder for me to do that is more of the mass is farther away from the axis of rotation, so it's a bigger moment of inertia. So objects can have different moments of inertia depending on what the axis of rotation is for that object. Every object has multiple, or most objects have multiple axes of rotation. So that's a little bit about that. That's how I affects things. I is essentially how hard it is to rotate something. Let me put you back where you're supposed to be. There we go. Oh. Okay. All right. So, let's get back to this now. So that's what moment of inertia is, a quick little overview of that. Now, back when we were talking about linear motion, in order to determine how many forces were acting, we would draw a free body diagram. We do a similar thing with angular motion. To determine what torques are acting, we draw another free body diagram, but here's the key difference. We draw the free body diagram for the entire object, as in we're actually going to draw the object now, as opposed to not just a dot. Now that it matters, the reason that we do this is because now we can show exactly where different forces are acting. So we can measure distances. By distance, we mean r. Okay? So, we're still going to draw free body diagrams, but they're different now. Now we're not just drawing a dot. Now we're actually drawing the shape of the object so we can show where the forces act, and so that we can indicate what distances, or what displacements, I should say, we're measuring for r. Okay, so that's going to be a little bit different. But again, the whole idea behind torque is it's kind of like the angular equivalent, or not equivalent, but analog. Analog means something that kind of pairs with something else. It's the angular analog of force. We're still drawing free body diagrams. We're still finding that torques. Just how we do that is a little different from what you've always done. Okay, let's get to some examples. Let's say that you have a meter stick that is pivoted about its end. So here's what I'm going to do first. I'm going to draw a picture, okay? Just like with forces, first thing you did was free body diagram. With torque analysis of something spinning or rotating, we're going to draw a picture. So meter sticks are nice and easy to draw. So I'm just going to draw a meter stick, okay? That's 1 meter. I'm going to put a little dot here, and I'm going to label this axis of rotation. Meter stick is pivoted about its end. That's the axis of rotation. What is the torque on the meter stick from a 2 kilogram mass placed at its midpoint? So if I put a mass here of 2 kilograms, what is the torque from that mass? Well, how does that mass affect my meter stick? The mass is going to push down the meter stick with a force equal to its weight, right? So the force that this object is putting on the meter stick looks like this, okay? It's coming from here, and it's Fg, which is equal to mg. And the displacement from the axis of rotation to where that force acts is this far. Here's r, okay? I know it's really tiny. Oh, you can't even see this, my bad. I apologize. Okay, there we go. So the idea here is, what is the torque on the meter stick from a 2 kilogram mass placed at its midpoint? For this first example, all we're doing is we're just examining, okay, how do we calculate individual torques? I want to calculate the torque from this mass, so I'm going to label this as torque from the mass. And I know that that's equal to r times F times sine of theta, okay? R is the distance from the axis of rotation, or the displacement from axis of rotation to where the force acts. The force is acting at that midpoint, okay? The mass is pushing straight down in that midpoint. So if this is a meter stick, well, that's got to be half a meter. So what I would write down is 0.5 meters times, now how big is that force? Well, we said it's mg, so actually I'm kind of substituting in different spots here. I'm going to change that to mg. And now let's talk about that angle, the sine theta part. Okay, sine theta, the theta is the angle between r and f if they acted from the same point. Here's r, here's f. They're clearly not tail to tail, but what if I moved them so that they were tail to tail? I would have r, and I'd have f, right? I just moved where the forces are. I just lined them up so that they're tail to tail. Nothing wrong with that, okay? This is very clearly a 90-degree angle. So we know that the sine of 90 is 1. So I'm just going to cross this off and put a 1 here. So the torque ends up being equal to 0.5 meters times the 2 kilograms from the mass times the acceleration due to gravity, 10 meters per second. Half of 2 is 1 times 10 is 10. The torque from the mass, in this case, is 10 Newton meters. Okay? Simple. What is the torque if the mass is moved to the opposite end of the meter stick? What if we move this mass over here? That looks ugly. Okay, what if we move this mass over here? Well, what's changed? The torque is still given by r times f times sine theta. The force is still the same. The force is still going to be the force of gravity equals m times g. So r times m times g times sine theta. Now let's evaluate. What changed? Well, now the force is over here. Okay? It's still the same force, but now the r is much bigger. So if it's all the way over here, r is now, well, if it's at the end of a meter stick, 1 meter. Times the mass, 2 kilograms, times g, 10 meters per second squared. And once again, you see that r and fg are still perpendicular. So times, oops, let's just cross this off. we know sine of theta is going to turn to sine of 90, which is 1. So, in this case, 1 times 2 is 2 times 10. The torque is 20 newtons per meter. It's twice as big. Think about what this means. If the torque is twice as big, then the impulse for spinning, I shouldn't use impulse, but the spinning or twisting or turning influence is bigger. Well, that makes sense, okay? We put it out here. It's going to be much harder to balance a meter stick with 2 kilograms out here than it was when 2 kilograms were right here. The torque is bigger. C says, what is the torque if the mass is moved to the same end as the pivot point? Putting it up here. We still have the same formula, but wait a second. Oops, that's an equals. If we put the mass here, and the force acts straight down, how far away is this mass from the pivot point? It's right on top of it. So R has got to be 0. And if R is 0, then this is no torque. 0 newtons times meters. What this means is that there's no influence, there's no spinning or twisting or turning influence if the mass is in this position because it's acting right at the axis of rotation. It's like trying to push open a door or pull open a door by pulling on the hinges. It's not going to work. When we come back, we'll do an example where we have multiple torques.